Hi everyone, this is Sheikh Roshan Jamir from CSE department from section E. The title of the PPT is Silicon Lattice Constraints on Structures of Interface States. Introduction. The impact of silicon lattice constraints on interface states is a critical area of study in semiconductors physics. Understanding these constraints provides insignificant the structure of interface states and their implications for electronic devices. Silicon lattice constraints are the restrictions imposed by the crystal structures of silicon on the impossible configuration of defects, impurities and interfaces states. Silicon has a diamond lattice structure, which means that each silicon atom is bonded to four nearest neighbors in a tetrahedral arrangement. The bond length between silicon atoms is 2.35 angstroms and the bond angle is 109.5 degrees. Any deviation from these values will result in strain and distortion in the lattice. Silicon lattice constraints. The crystalline structure of silicon imposes constraints on the arrangement of atoms, affecting the behavior of interface states. These constraints influence the electronic properties and performance of semiconductor devices. Some examples of silicon lattice constraints are the information of dangling bonds at the surface of interface of silicon, which are unsaturated bonds that can act as trap states for carriers. These dangling bonds can be passivated by hydrogen or other atoms to reduce the interface state's density. The incorporation of dopants or impurities in the silicon lattice, which can alter the electrical properties of the matter depending on the size and valency of the dopant atom. It can either substitute for a silicon atom in the lattice (substitutional) or occupy an interstitial site between silicon atoms (interstitial). Substitutional dopants tend to cause less strain than interstitial dopants, but they also have lower diffusion coefficients. The formation of dislocations, which are line defects that occur when the lattice is distorted by external stress and thermal mismatch. Dislocations can act as sources or sinks of carriers, depending on their type and orientation. Dislocations can also interact with other defects or impurities, creating complex defect structure. Interface states. Interface states are localized energy levels at the interface between different materials. The distribution and density of these states are influenced by the silicon lattice constraints, impacting performance. Interface states are special modes that exist at the boundary of two different media, such as photonic crystals, metasurfaces, and mirror lattices. They can have interesting properties, such as band-folding bound states in the continuum or quantum emission manipulation. Lattice constraints are the conditions that the interface states have to satisfy in order to exist and to be stable. They depend on the geometry, symmetry, and material parameters of two media. Quantum mechanical effects. The silicon lattice constraints give rise to quantum mechanical effects that govern the behavior of interface states. Understanding these effects is crucial for designing advanced semiconductor devices. Experimental techniques. Advanced experimental techniques such as scanning, tunneling, microscopy, and spectroscopy are used to probe the structure and behavior of interface states affected by silicon lattice constraints. I searched on the web for experimental techniques for lattice constraints and found some relevant results. Here is a summary of what I learned. Lattice structures are a class of cellular materials that have many advantages over other types of cellular materials, such as foams and honeycombs. They have low relative density, high strength, energy absorption, and vibration reduction. Lattice structures can be divided into two categories: uniform and non-uniform. Uniform lattice structures have the same unit cell throughout, while non-uniform lattice structures have varying unit cells that can create gradient and optimize the topology. Lattice structures can be fabricated by different methods, such as traditional processing and additive manufacturing. Additive manufacturing (MAM) is a promising technique that can create complex and customized lattice structures with high precision and efficiency. Some examples of AM methods are selectively laser melting (SLM), stereolithography (SLA), and fused deposition modeling (FDM). Lattice structures can be designed and optimized by various methods, such as geometrical unit cell based mathematical algorithm generated and topology optimization. Geometric unit cell based methods use predefined shapes to construct the lattice structures, such as Kelvin, rhombic dodecahedron, and truncated cuboctahedron. Mathematical algorithm generates the methods use algorithms such as Voronoi tessellation, Delaunay triangulation, and space-filling curves to create the lattice structures. Topology optimization methods use mathematical models and optimization algorithms to find the optimal distribution of material in the lattice structures. Modeling and simulations. Computer simulations and theoretical models are employed to study the influence of silicon lattice constraints on interface states, providing valuable insights for device optimization. Modeling and simulation of lattice constructions are important topics in engineering, physics, and mathematics. Lattice structures are composed of repeating patterns of cells that can have different shapes and sizes and materials. They have many advantages over conventional material such as lightweight, high strength, energy absorption, and vibration reduction. Lattice structures can be fabricated by various methods such as additive manufacturing (AM), such which allows for complex and customized designs. Implications for device performance. The understanding of silicon lattice constraints on interface states has significant implications for the performance and reliability of semiconductor devices, shaping the future of electronics. Optimizing device design. By accounting for the impact of silicon lattice constraints, engineers can optimize the design of semiconductors devices, leading to enhanced performance and functionality. Future research directions. Continued researches into the impact of silicon lattice constraints on interface states will drive innovation in semiconductor technology, paving the way of next generation electronic devices. Challenges and opportunities. addressing the challenges posed by silicon lattice constraints, presenting opportunities for breakthroughs in semiconductor physics and device engineering, opening new avenues for technological advancement. Key findings: the study of silicon lattice constraints has revealed key findings that deepen our understanding of interface states and their implications for semiconductor devices, offering valuable insights for industry applications. Conclusion: the impact of silicon lattice constraints on interface states is a pivotal area of research, with far-reaching implications for semiconductor technology. By unveiling the intricate relationship between lattice constraint and interface states, we can drive innovations and shape the future of electronic devices. Thank you.